This lecture is going to be about Suvat equations or kinematic equations in uniform acceleration. I wanted to also bring up the unit overview that we have covered so far in the winter break assignment. But also, we're moving through some of this kind of fast, so I'm just going to kind of do some checkoffs as we go. So the main objective is can describe 1D motion qualitatively using words and quantitatively using graphs and equations. This day is going to focus on the equations part. But let's just go through this and make sure we are checking this off as we go. So we can identify the coordinate system used to describe motion, including positive and negative directions. Yeah, so we've done that last class with positive and negative graphs. We've determined instantaneous and average value for velocity, speed, and acceleration. Yeah, we haven't done average acceleration, but it's the same concept as average velocity, so I think we're okay there. Solve problems using equations of motion. That's what we're doing today. So this is what we're doing today. Translate between displacement time, velocity time, and acceleration times using slope and area under the curve. That's what we did last class. Interpret position time, velocity time, and acceleration time. So we've done that last class. Determine acceleration of free fall to be g equals 9.81. We did that last year, so I'm going to check that off. And solve free fall problems using equations of motion. We are going to do that today as well. So we're going to knock out this first objective in these first 2 days. So let's move forward. So they're called Suvat equations because that's the variables we use. We identified S before. S was displacement. And it's always going to be measured in units of meters. U and V are our velocities, actually. But U comes before V, so this is going to be our initial velocity. And the units are meters per second, and it is a vector, so it has a direction. This is going to be our final velocity. So, of course, if we have an initial and a final, that means time has to pass. A is for acceleration. And the units are meters per second squared. And t is time in units of seconds. So that's why they're called Suvat equations. One thing to remember, acceleration, because we're going to use this later, is equal to the change in velocity over change in time. Or another way of writing that is like v minus u over t. So in these videos and in my OneNotes, I'm going to link different videos you can watch relating to the concepts that can maybe help you make sense of this. So I've got a video of falling off a cliff or relative motion while moving. That's good just to kind of make sense of relative motion. And then in free fall, this Mythbusters bullet, it shows a bullet dropping and a bullet being shot from the same height. And it's just a cool Mythbusters video about how the acceleration downward is the same for any object, whether it's moving horizontally or not moving. All right, so we got our basics down. I've got 2 graphs right here. And in these 2 graphs, my goal is to try to find 4 equations. Really, it's actually we're only going to get to 3. The fourth I'm just going to give to you because it's kind of hard to derive. The first one is actually rather easy, and it stems from this right here. If A is equal to v minus u over t, then I'm going to solve for v. And if I do that, if I multiply t over, I get a times t is equal to v minus u. And then I add u over, and I get a t plus u is equal to v. And this is going to be our first equation. V is equal to u plus a t. So this is in your data booklet. And it's one of the first equations of kinematics. I also suggest whenever we do math using variables, not numbers, it's good for you to identify what the equation means in words. So this is a good practice, right? So I would say this as the final velocity is equal to some initial velocity plus some, a change in velocity that is found by finding how long an object is accelerating for over a period of time. Something like that, right? AT is really the change in velocity due to just the product of acceleration and time. Okay, so we're going to use this graph to determine the second equation. Now, in the previous video, we've learned that we could find the displacement using the area under the curve. And so let's look at it here. It has some initial velocity, it has some final velocity over some time period that ends right here. And I'm going to shade this first area in. And I'm going to define what that area is, right? That area is just u times t. So that right there is u times t. Let's see, let's go a different color. Let's go orange. And I'm going to find this area. Well, what is that area? Well, it's a triangle, so I know there's a 1/2, right? And let's actually do this. Let's downward, yeah. And then, so this right here is 1/2 base, which is times t, times the height, which is v minus u. And this, when you add those together, you should get s. So s is equal to ut plus 1/2 v minus u times t. All right, this is kind of an ugly equation. So I'm going to want to substitute something in. And I see actually up here in my acceleration, at this area right here, I have at is equal to v minus u, and I have a v minus u here, and I have a v minus u there. So I'm going to actually be able to substitute this at portion into that part. So I'm going to change that to a times t, and the rest of the equation is the same. But this gives me my final equation. S equals ut plus 1/2 a times t, so that t is squared. And this is the second equation we'll find. This is in your data booklet as well. Right, so right now we have equation 1, we have equation 2, and there's 2 more equations we need to get. The third one is actually, we've already kind of seen it, we just need to process, we need to do some algebraic manipulation. So this equation is the same one that we had right here, the s equals ut plus 1/2 v minus u times t. We just need to solve for this, simplify this. So I have s is equal to ut plus, and I have what, v over vt over 2 minus ut over 2. I just multiplied t by both v and u, and then I multiplied 1/2 by both v and u. So I do see like terms in here. I see a ut right here, and that's like a 1 ut, and I see a 1/2 ut. So this is like if I were to write a 2 and a 2 on the top, right? 2 ut over 2 is the same as ut. And I see I can put together my like terms. So I end up with 2 ut minus ut over 2 plus, actually, all of them have a common denominator, plus vt. And so this ends up being s equals ut, right? ut plus vt over 2. And I'm just going to factor out the t now to get this final equation that you'll see u plus v over 2 times t in your data booklet. This is your third equation in your data booklet. And this one actually has some relevance to the graph. And so we didn't actually have to solve for it if we didn't want to. We can think of this through some sort of transforming the graph to make it fit the equation. U plus v over 2, well, that's the initial velocity plus the final velocity divided by 2. So this right here, u plus v divided by 2, actually let's do that in a different color. Let's do it in orange, sure. U plus v over 2. That is your average velocity. So if we look on the graph, where is our average velocity? Well, it's halfway between u and v, so it's right here. So if u plus v over 2 is our average velocity, that value, and you multiply it by some time, well, that means that this is time right here. So it's this graph right here. This area is what that equation is saying. And so this area, this triangle that is not inside of the area S, is found on the opposite side. It's like moving this triangle right there, and then you have this average velocity times time. It's uniform acceleration, which means acceleration is constant, so this is why we can do this. And that's your third equation in your data booklet, and then I just have to give you the fourth one. So the last one is v squared equals u squared plus 2as. There's some algebraic manipulation you can do to find it, but it's unnecessary. So I'm just going to give it to you. So this is your fourth one in data booklet. Okay. All right, so I've organized them in 1, 2, 3, and 4. They don't have to actually be labeled 1, 2, 3, and 4. These equations would be good for you to write down somewhere because you're going to be using these throughout all of this unit. And I want you to look at these equations and try to identify why do we have 4? What is different about each of these equations? You can pause the video, look at them, and try to think about why we need these 4. And if you have an idea, there is no S in this equation. There is no V in this equation. There's no A in this equation. And there's no T in this equation. S, V, A, and T. Every single one has a U, though. We need to know the initial velocity. But there is no displacement in 1, velocity in 2, final velocity in 2, acceleration in 3, and time in the fourth equation. And that's why they're useful. That's why we have 4 of them. All right, I've got an example question I'm going to work through. We're going to work kind of together on this. You're going to pause, solve, so forth. So Batman is drag racing the Joker in a 100-meter race. The Batmobile accelerates at a rate of 8 meters per second squared. How long does it take for the Bat to finish the race if we assume constant acceleration? And now I'm going to ask you to pause the video and solve. But before that, there are some problem-solving techniques I want to go through, and it has to do with just identifying variables and making sure you read through, like in between the lines. So they are drag racing. We know we have a 100-meter displacement. We have an 8 meters per second squared acceleration. And so far, like in terms of numbers, that's all we technically know from the problem explicitly. So on the side, we're going to want to write all the variables we know. Now, there is something hidden in here, and it's the fact that it's a race. And racers start at a starting line, and they start with a 0 velocity. So we can kind of implicitly pull out that it's Batman's initial velocity is going to be 0 meters per second. Once you have this as S, A, and U, then you go up to your equations that you have written down somewhere, and you try to identify what do I need? Which equation can I use? And you also need to know what you're trying to solve for, right? So how long does it take? So we do need a time. So we have S, A, U, and T. We do not have the final velocity. So I think I'm going to go with equation number 2. Go ahead and pause and solve this, and I'll have it written out in a second. All right, and I have the answer right there. Using the numbers, t is equal to 5 seconds. All right, so that's kind of your basic, very easy kinematics equations, but it could get a little tricky. This next problem is going to introduce some trickiness. So unfortunately, the Joker's car can only accelerate at a rate of 6 meters per second squared. The Joker loves to tie the Batman to continue the good versus evil charade, and the Joker knows he doesn't have the same acceleration, so he needs to start the race with a non-zero initial velocity. What initial speed should he have in order to tie the Bat? This is where you would need to kind of have, I think, a drawing. So I would draw a Batmobile. Now, don't laugh there. That's my Batmobile. Ooh, so cool. And I know that its initial velocity is 0 meters per second, and I know at some point in time we'll have s is equal to 100 meters. And then there's the Joker, which I guess can only be green. That's and his is just a van. I don't know why. We also know it's 100 meters, so I can kind of extend this line down. And I don't know. It's definitely moving, right? Because this is the starting, and we don't know u. So we know it takes 5 seconds for the bat to finish the race. So I'm gonna want to identify these. Let's see if I can. Yeah, perfect. I'm gonna say, okay, I do know that t is 5 seconds. I know that my bat has 0 meters per second. I'm not sure if I need that. I just know that the Joker is going to need to finish the race in 5 seconds, right? And we have the Joker's acceleration, which is 6 meters per second squared. And we know I think that's what we know. I'm going to pause the video. I want you to solve this. I'm also going to solve it, and we're going to check once we're together. And I'm back, and I've solved it below. So let's see if you did the same thing. So I used the same equation, just switched some numbers around, and I ended up with u is equal to 5 meters per second. Another 5. All right, I'm going to only work through one more problem with you, and then I'm going to let you solve the rest of the guided practice. So in this situation, I'm going to want you to use a graph to support your mathematical problem solving. So we have a penny that's dropped from a height of the Empire State Building, and after 9 seconds, the penny hits the ground. Acceleration due to gravity is 10 meters per second squared, so that means the penny's velocity is going to increase 10 meters per second every second. And calculate the height of the Empire State Building. So I know that t is equal to 9 seconds. I know that u is equal to 0 because it's being dropped. I know that a is equal to 10 meters per second squared. And there might be some discussion of should I make it negative because it's going down. And I'm not right now because down is the only direction the penny is going. If the penny were to be moving and be like tossed upward, then we'd have opposing directions and we would need positives and negatives. But I'm going to kind of cheat a little bit and just say down is positive. That's what I'm going to say. And then I need to find s. Oh my gosh, it's the same equation, isn't it? Looks like it. S is equal to ut plus 1/2 at squared. So s is equal to 0 because the u is 0, plus 1/2, a is 10, and time is 9 squared. So that looks like s is equal to, I think, 405. Let's confirm that. Let's see if I did that right. So I'm going to go on here and say, oh, 1, 2, 3, 4, 5, 6, 7, 8. No, we don't have 9 seconds in that avenue. Let's do half of that. So this is 2 seconds. 4, 6, 8. So right here is going to be 9. It's traveling 10 meters per second. So I'd have to go up. Like, let's call this, I think this would be 40. And this would be 20. Because after 4 seconds, it should reach 40 meters per second. After 6 seconds, it should reach 50. So after 8 seconds, it should reach 80. After the 9th second, it should reach 90. So it's like right here, right? Somewhere right there. And that's 90 at 9. So I'm going to draw a line between, oh, it's right. OneNote does not like when I do that. And I'm going to find the area under this triangle to see if my S matches up with 405. So I have 90 times 9 divided by 2. And that looks like the exact same math that we just did. 90 times 9 is 800. Was 9 times 9 is 81, so 9 times 90 is 810 divided by 2, and that's 405 meters. And that checks off. So that's the type of way I want you to check your answers using the graph. Now, there are two more problems that aren't shown here that you've been linked with the PDF in class. I want you to work on those. The one difference you might have to be aware of is deciding which direction is positive, which direction is negative, and it's just good to say up is positive and down is negative if an object is traveling both up and down in one single motion. Yeah. And that's it. I'll see you in class.